Dating deformation, or applying absolute dating techniques to faults and folds. So usually in geology, when we talk about absolute dating, we're talking about dating the ages of formation of different types of rocks. However, in structural geology, we can use those same techniques to date the ages of deformation structures and hence the ages of the deformation events that produced said structures. This can be complex, or the assumption that we always make is that the measured ages of structures represent ages of resetting due to deformation, which can be complicated by factors such as the closure temperature of the system, diffusion of elements, annealing of fission tracks, or the presence of fluids. Luckily, there's a whole host of different techniques that have been developed for dating rock deformation, which we can apply then to date rock deformation. And microscale observations are extremely important in helping us justify the assumption that we are actually measuring the ages of deformation structures, not just the age of some random feature in the rock. So what I want to talk about today more specifically is how do we apply absolute dating methods to faults and folds, and even more specifically about folds and pseudotachylite in faults. So our first example comes from Japan, which is of course an extremely tectonically and structurally complex region, as it straddles the boundary between the Eurasian plate and the Pacific plates. And we're going to be looking at the vicinity of the median tectonic line, which is a dextral strike-slip fault system running through the southern half of Japan. So this example is more specifically from the Asuke shear zone, located right next to the median tectonic line over here. And what was done is that samples were taken from across the shear zone, from the undeformed host rock, from the pseudotachylite in the middle of the shear zone, and from the flanking cataclasites at the edges of the shear zone. And these were all dated using fission tracks in entrained zircon crystals, shown in black, and with uranium lead dating, shown in white. And we can make two key observations. First of all, it's important what technique we use to date deformation, because the uranium lead ages are essentially unaffected by deformation here. Secondly, it's important that we know that, or that we choose what we're actually dating very carefully, because as we can see, only the pseudotachylite has been completely annealed or completely reset by the deformation event. So only the pseudotachylite gives a true age of deformation, whereas the flanking cataclasites give only a partially reset and hence incorrect age. So it's very important that we know what we're actually dating, because otherwise the age is meaningless, really. Quite an interesting example from the Histros-Nossa shear zone in central Norway shows, the shear zone shows synkinematic myelonites and pseudotachylite. Sorry, which is of course a bit of a problem, because myelonites are formed in the ductile or rheologically ductile regime at great temperatures and depths, whereas pseudotachylites are formed at shallower depths in the brittle regime. And it was thought that this might be a later overprinting during exhumation. What was done to test this was that white mica crystals in the rocks were dated using argon dating, and it was shown that there's an approximate 110 million year age difference between the myelonites and the pseudotachylites. And this is far too long of a time to have been due to overprinting during exhumation, because exhumation in this region has been shown to have been much faster than 100 million years. Instead, this was interpreted as two different unrelated deformation events. Firstly, related to the Scandian orogeny, the Scandian orogeny deformation event produced the older myelonites in the rheologically ductile regime. Then exhumation occurred, and later, related to the west-east extension of the Atlantic, the shear zone was reactivated to produce pseudotachylite at the surface instead. And this is quite important in showing that dating rock deformation, or dating the deformation structures in rocks, can be used to not only separate different deformation events in time, but also in different rheological regimes. So moving on to folds, this is a classic thin-skinned tectonic example of a series of folds in the Mexican fold thrust belt in central Mexico. And what's been done here is that illite crystals have been dated using argon dating in clay-rich layers in chevron folds. And the complication here is that there are two types of illite present. There's detrital illite, which was present before folding, and which we are not interested in this context. And there's orthogenic illite, which was formed synkinematically in the flexural slip planes of the limbs, or the limbs and the hinges in this case, of the chevron folds. So what can be done is that we can separate them into different size fractions with different proportions of the two polytypes of illite and distinguish between those using X-ray diffraction to produce a plot like this, where we have the percentage of detrital, or the proportion of detrital illite against age, such that at 0% of detrital illite, we must have only orthogenic illite, hence giving us the age of the folding. This was done for a series of folds going roughly west to east across the transect in central Mexico, showing that the deformation is, first of all, highly localized, and second of all, there is a younging of deformation structures towards the east, such that the oldest folds are in the west and become progressively younger eastwards. Now, this is quite interesting because the critical taper model for orogenic wedges states that the orogenic wedge, or rocks in the orogenic wedge, are at failure everywhere in the orogenic wedge. And well, this clearly isn't the case here because we have highly localized deformation and failure, essentially. This was explained by the influence of chevron folds. So when chevron folds become tighter, they kind of lock in place, making the rock itself harder. So as we start with deformation in the west of the orogenic wedge, the chevron folds lock in place, making the rock harder. Hence, it is more energetically favorable to deform the softer or weaker rocks further eastwards. And this was interpreted to have happened in three different deformation events, one of which is, I guess, hidden by my head here, which is not ideal, but anyways. Yeah, this basically shows this is a composite orogenic wedge, which deformed in not only highly localized events, but in different events as well. And this shows that dating deformation dating techniques are very useful in building up a regional deformation history of a region, I guess. The two problems with illite dating are that, first of all, illite is an extremely small mineral, so it's difficult to target. And secondly, illite is quite vulnerable to later overprinting. An example from the Sino-Korean Craton, which is a very complexly folded region in northern China, used argon dating of muscovites instead. And textual evidence from optical light microscopy and scanning electron light microscopy was used to show that these muscovites are indeed synkinematic. So these are in the flexural slip plane, and they are highly parallel and systematically aligned with the lineaments of the folds themselves, showing that they are synkinematic. So what was done is that these were dated and grouped according to deformation regime, or tectonic regime rather, to produce this plot here. So it was interpreted as three separate deformation events split across three different tectonic regimes. And this is, of course, extremely useful for building a picture of how, well, it's first of all extremely useful for building a picture of regional, or building a regional deformation history rather. And secondly, it shows the importance of different types of microscopy and textural relationships in showing that we are actually dating a deformation event, not just any random minerals willy-nilly. To circle back to the research question, there's 3 points I'd like to make here as concluding remarks. Firstly is that understanding resetting is key. As the Japan example showed, we need to be sure that the system has been entirely reset, or we're going to be measuring essentially an incorrect age. What was I going to say? Lost my train of thought there. Anyways, textual evidence is, of course, also extremely important in justifying the assumption that we're actually measuring deformation structures. As shown in the China example, we need to be sure that these features were actually formed during deformation, because otherwise the age we measured doesn't really mean anything, at least in the context of structural geology. Thirdly, absolute dating methods are very useful in mapping out deformation not only in space but also in time. So as the Norwegian and Mexican example show, that they allowed us to build a regional deformational history by dating different deformation features and relating those to each other. So that's me done. Here are my sources, and thanks for listening.